four subunits. There are four porphyrin groups. Each of these contain a little iron molecule, oxidized iron molecule in there. And each one of those four irons can bind a diatomic oxygen molecule. And as you look at the conformational change in the animation here, we're watching that hemoglobin shift from oxyhemoglobin to deoxyhemoglobin. And by that we simply mean whether it's binding and saturated with oxygen versus when it is not. And of course, it is critical, it is absolutely critical that this hemoglobin molecule, this transporter or truck for oxygen in the blood, be able to reversibly bind oxygen, because the general idea is as a truck, you want it to take on the load in the lungs, you want to fill it up with oxygen in the lungs, and then you want this molecule to be able to unload the oxygen where it's required in the peripheral tissues. So that's the general argument we're going to make. Now, the way we're really going to simplify this is I want you to sort of think about this molecule as being sensitive to a number of critical physiological parameters. In other words, what tells this? You can imagine this as having a little brain and deciding whether to take on oxygen or not. What physical stimuli, what physical characteristics are going to incline this hemoglobin molecule to bind oxygen, and conversely, what physical stimuli or characteristics would dispose the hemoglobin molecule to unload, dissociate from the oxygen? Well, the way that I would invite you to think about this is just to think about some of the characteristics of living, respiring, thriving cells. So let's say we have, I don't know, this room is a cell once again. The room is vital. The room is metabolizing energy. We're generating ATP. We're taking in oxygen, which is hint number one. We're consuming oxygen, and we're also yielding or giving off carbon dioxide. And as we're doing that, I think you'd probably agree that in the process of oxidizing the fuel, and by oxidizing we mean taking oxygen, mixing it with some carbohydrate fuel and producing energy, like your car engine, you're going to be generating heat. So if you look up here at these three characteristics, and there are some others we can talk about, but these are the three I want you to focus on. These are the three principal characteristics which would signal the hemoglobin molecule, hey, there's respiration going on in the vicinity, and respiration requires oxygen. So these characteristics, these physical stimuli, would induce the hemoglobin molecule to unload or dissociate the oxygen. And of course, the opposite of these would induce the molecule to take on the oxygen. And so you might imagine this molecule traveling through the bloodstream, and the closer it comes to elevated temperature, of course, there's a lot of factors that might elevate temperature, but one of these would be increased metabolism. As the CO2 levels go up, as the cell respires, takes in oxygen, gives off CO2. I just saw the other fellow standing back there, he's very distinguished. And we're going to find there's something called Bohr's law or Haldane's curve that yields a relationship between CO2 and hydrogen ion concentration. So very simply, the closer this thing gets to a respiring cell, these things should change in the direction that we see them. And as that happens, the oxygen should be released from the hemoglobin. Now, if that's true, let's look at some of these. I think a lot of you are probably familiar with these oxygen hemoglobin dissociation curves. They go by a variety of names. But really what I want you to be able to do is explain these curves to me on a test or certainly in the course of your practice. Now, we need to make some simplifications because we don't have time to work through all the complexities of these. But if you look at the axes here, the horizontal axis, this is fairly straightforward. It's just PO2, it's partial pressure of oxygen. Partial pressure of oxygen in the blood. And the way we're going to simplify this percent oxygen saturation of hemoglobin, so we're talking about the extent to which the hemoglobin in the blood is binding, and all of its binding sites are occupied by oxygen molecules. Let's sort of construct the following simplification following model. As we pointed out, that hemoglobin molecule has 4 binding sites for oxygen. If the hemoglobin molecule is completely saturated, then all 4 binding sites are going to be bound, yet be occupied. If none of them are occupied, then of course we're at 0 saturation. 50% saturation, according to the simplified model, would suggest that about half the binding sites, 2 of the 4 binding sites, are occupied. So that's how I would have you appreciate this oxygen hemoglobin dissociation curve. And what you'll notice, a couple things, although this particular example perhaps at the best, is that, first of all, the oxygen hemoglobin curve is sigmoidal, has sort of an S shape. And you can see, depending upon, again, the extent, that the curve is relatively steep shortly above 0. So it's a very small range, in most cases, a small range in partial pressure of oxygen that produces a dramatic change in the saturation. And then you'll also notice that depending upon the property that we're talking about, the curve tends to level off. We can look at some of these others here, sort of approaches the asymptote there at 100. But it levels off such that in most cases the line is fairly straight as we get up, 75, 80%. But we're going to talk about this in a little more detail in just a moment. Where that line begins to level off, partial pressure is still maybe about 50 millimeters of mercury. So let's go back to this first one here and sort of work through some of this. So let's focus on the partial pressure of oxygen here, and I put a vertical line here at 40. Any particular reason I would pick 40 for my vertical line as a point of reference? 40 millimeter partial pressure of 40. We've run across that number before.
The venous partial pressure.
All right, so we're talking about the partial pressure of oxygen in the blood returning to the lungs, And as you can see, as we go up we move up that partial pressure, we'll just use that as our reference point. We come over here at 100 or wherever. We'll use that as our reference point. Notice we have 3 lines. We have a blue line, a purple line, and a red line. And the blue line is 20 degrees, and the red line is 43 degrees. Okay, so you would agree as we go from the blue to the red, the temperature is increasing. So let's do this. Let's go there, and then we'll go up to the blue line, and we can see that we have something like this. So as we increase the temperature, what happens to the ability of the hemoglobin to bind and retain oxygen? So red is high temperature, blue is low temperature. So this is higher, this is lower. So when I go from the blue line here to this point, what happens to the ability of the hemoglobin to bind oxygen? It decreases rather dramatically. All right. So what we're saying is, hemoglobin, as the temperature increases, tends to unload, dissociate from oxygen. We call that a shift to the right. A shift to the right simply means that the hemoglobin is releasing oxygen. A shift to the left would mean that the hemoglobin is taking on oxygen. So let's look at this one. This is the effect of ambient carbon dioxide concentration on the ability of the hemoglobin to bind oxygen. Here's our 40. We'll use that as a reference again. The blue line is a partial pressure, CO2 partial pressure of 20 millimeters. The red line is 80. So once again, as we go from we'll just use the 40 as our reference. We go from the 40 to the 80. What happens to the oxygen saturation of the hemoglobin? Increases or decreases? Going from the blue line to the red line. Decrease. All right, so just make sure once again, as we increase the partial pressure of CO2, the ability of hemoglobin to bind oxygen has diminished. And once again, you would agree that going from the blue line to the red line is a shift to the right. A shift to the right simply means that the hemoglobin is dissociating from oxygen.
I'm sorry, can you say that again? Is the increased partial pressure of CO2?
Yeah, remember, before I do that, remember our general argument. We're a respiring cell. Everybody in this room is most of you are respiring, most of you are alive. And as alive, you are, did you want me to answer the question or?
Yeah.
Okay. As you're alive, you're breathing out oxygen, you're breathing out CO2, you're taking in oxygen, and the temperature is going up. Same thing here. We're going from the blue line to the red line. The CO2 is going up, and as it increases, that's an indication of vitality, an indication of cellular respiration. But as it does so, we're going from about 85 to what number is this? Maybe 55% saturation. So 55 is lower than 85, so there's less oxygen binding of the hemoglobin in the higher CO2 situation, lower CO2 situation. And then we're going to see there's a number of principles that are used to describe this relationship. We talked about a little bit when we talked about the carbonation of your Coca-Cola or your Pepsi or whatever. What tends to happen is that as CO2 concentrations in water increase, the acidity of the water will also increase, or said another way. As the CO2 levels go up, pH goes down, and pH is an inverse scale. So in this particular example, we have three lines, yellow, whatever color that is, brown, and green. We'll use this as a reference again, the 40. And so as the pH drops, as the blood becomes more acidic, bear in mind, that's going to be associated with changes in CO2. As the blood becomes more acidic, going from the yellow line to the green line, what happens to the ability of hemoglobin to bind oxygen? Increases or decreases? As we lower pH, hemoglobin unloads the oxygen, releases the oxygen, and so doing, is making more oxygen available to the respiring cells. So make sure you understand the relationship between saturation, again, we'll say it's about 84 or something, 62, as we go from 7.6 to 7.2. And this would happen for a number of reasons. It would happen primarily because of the increased CO2 concentration in the blood.
Would you say the opposite is also true? If you have a lower pH, would the cell have a hard time picking up oxygen?
Yes, that would always be true. But generally, that will not be the case. Why would that not be the case? Louise is asking if the pulmonary blood has a low pH, the hemoglobin would have a hard time taking on oxygen. Why is that not likely to be the case? What is the cause of the low pH here? Yeah, and so normally, if the patient is respiring normally, the O2 to CO2 ratio in the lungs should increase. Any questions then about the oxygen hemoglobin dissociation curve? I think most of you have encountered this before. And be sure you know what we mean by a shift to the right and a shift to the left. Speaking of a shift to the left, one of the more insidious examples of this is carbon monoxide poisoning. And you're looking at a deceased individual in the lower right here. This individual suffered from carbon monoxide poisoning. He clearly is not cyanotic, right? There's no evidence of bluish skin. In fact, you have the carbon monoxide lividity. So that's a curious phenomenon. He's effectively hypoxic, and yet the skin would appear otherwise. The skin would suggest, in fact, a hyperperfusion of oxygen. So how do you explain this? Well, there are two characteristics of carbon monoxide that we need to pay attention to. Number one, carbon monoxide will outcompete oxygen with respect to hemoglobin binding. So, in other words, hemoglobin seems to prefer carbon monoxide to O2. So you might therefore ask, how would you treat a patient if you had the opportunity that was suffering from carbon monoxide poisoning? And then number two, the other even more insidious aspect of carbon monoxide poisoning once that carbon monoxide has bound to the hemoglobin molecule, it effectively prevents the hemoglobin from releasing oxygen. So it almost locks the oxygen into place. What's the problem there? Remember that hemoglobin must be able to reversibly bind oxygen. If it can't take on the oxygen and release it, then it's not doing a darn bit of good. So what we're saying is carbon monoxide prevents or inhibits the hemoglobin from releasing the oxygen. So the net effect of carbon monoxide is to shift the oxygen hemoglobin dissociation curve to the left. The patient typically would not have increased ventilation, and as you can see in the image here, the blood is quite red. In fact, one of the fellows who came up with the conservation of energy principle down in the tropics noticed the color of the blood and started thinking about why the blood is so red in the tropics, and began formulating. He was one of 3 people that formulated the theory of the conservation of energy at about the same time in the middle 19th century. But be sure you know what we mean by a shift of the curve to the left and how carbon monoxide tends to achieve that. Of course, this has practical implications when you go shopping for meat in the supermarket. What are you looking for?
Veggie burgers.
You probably don't want it to stink, although that may be a better test in light of what is actually happening. Most of the meat, at least until recently, some of the grocery chains have argued they no longer do this. I'm not sure I believe that. But they expose the meat to carbon monoxide. What effect would the carbon monoxide have on the appearance of the meat? Nice and red, yeah. So how are you going to know if your meat is truly fresh or not? Pick it up and smell it. Right? Take the wrapper off. Give it a whiff. Not sure they'd let you do that or not, but I just use this as an illustration of the effect of carbon monoxide on the hemoglobin.
How do they do it post, do they do that after the cow has been slaughtered?
Yep, it wouldn't matter as long as the red blood cells are there. That's the displacement of or the binding as long as that hemoglobin is there, that's still going to occur. Yeah. Yeah.
So what would be the treatment for carbon monoxide poisoning? You can't just give them oxygen.
Well, when you say you can't give them oxygen, why?
Like,
If you
give pure oxygen to someone who has carbon monoxide poisoning.
Sure.
The hyperbaric chamber, you increase the partial pressure of oxygen, give it to them.
So what he's saying is that you can give them oxygen. You increase the partial pressure. Under what theory? What would be the theory behind that? So, for example, if you've ever had a dog, dogs like to drink antifreeze. I like the taste of antifreeze. If you or your animal drinks too much antifreeze, what's the typical? It's ethylene glycol. It's a glycol. It's a diol. Yeah, you can sometimes use alcohol as a competitor. Same idea here. It's just competitive. It's just competing for the sites.
What is the picture of the person that died from carbon monoxide? Why the skin on the bottom is so yellow?
I don't know.
Oh, okay.
Anybody know? My guess would be that he was on his stomach when he died, and now they've turned him over. But I don't know.
Okay.
Some of you may have more insights than I do. In other words, the blood would have pooled in the direction. All right, let's talk a little bit about the renal hormone EPO, erythropoietin. It's been in the news recently with respect to, the Tour de France just concluded, right? And it's always a lively topic of discussion. In fact, I think they're suggesting that maybe one of the medal winners. In fact, I meant to find the news report because it's relevant. But anyhow, I'll look for that later. I saw it a few days ago. They have some devious process to achieve this. Anyway, what is EPO? Erythropoietin, as I say, is a hormone that is, for the most part, in adults, is generated by the kidneys. There's some fetal production by the liver, and it has 2 general effects. But both effects are to increase the oxygen carrying capability. It increases the number of red blood cells, the relative abundance of red blood cells, basically enhancing or increasing the hematocrit. And it also increases the concentration of hemoglobin in the blood. Once again, the net effect of both processes is to significantly enhance the ability of the blood to transport oxygen. So the primary stimulus for EPO synthesis is hypoxia. And we'll talk more about that later. But basically, anything that would induce peripheral hypoxia is likely to cause increased synthesis of EPO. Now, one of the problems with this, of course, you can think about what would happen if there's a very high concentration of EPO in the blood. The RBC count is going to go up. And when that happens, there is the increased risk of something called polycythemia. Polycythemia implies, I think it's also called erythrocytosis, implies that there are more red blood cells than normal traveling in the blood. The hematocrit is elevated, and thus the viscosity of the blood is increased. What do we mean by viscosity? Yeah, the relative thickness basically is defined as the ability, the readiness with which a fluid flows. You can compare molasses or honey to water, for example. So we're making the blood thicker in polycythemia, and that's increasing the workload on the heart. So there are any number of ways that the hematocrit and the hemoglobin levels in the blood can be changed, can be altered. For example, a lot of these cyclists were doping not merely with EPO, but with what else? What? Well, yes, but their blood was enhanced with, what were they doing there? For example, you read the stories of Lance Armstrong on the bus late at night, and they'd all be laid out with the transfusions, putting their former non-depleted blood back into their body. But oftentimes that blood would also contain something we talked about earlier. Is there any hormone you can think of that also increases? I'm sorry?
Growth hormone?
Growth hormone has a number of effects. I don't know that increasing the hematocrit would be prominent among them. There is one hormone that does that we did talk about clearly. Yeah, testosterone, the androgens. So often they'll create a cocktail or soup of EPO and testosterone. Remember, males have a higher hematocrit than females for that reason.
Can you reach similar, the same results by training high altitudes or sleeping in hyperbaric chamber?
Oh, well, let's be careful how you pronounce that. You're exactly right. That was the third thing I wanted to touch upon. I think George was talking about this too. So Luis was talking about, what did you say, hyper or hypo?
Hypo.
All right, so hypobaric chamber, yeah. So the idea there, and by the way, it's a fascinating, if any of you are interested in this topic, you might maybe for your research project or something, look into the ways that human beings have adapted to living at high altitudes. It's not all different humans in different parts of the world have adapted in different ways. So what would happen? How might you compensate? And the biologists have two terms: we have acclimatization and adaptation. But how might you adapt to moving to a very high altitude, which, by the way, is going to be different from sea level in what dramatic fashion with respect to your respiratory physiology? What's really changed there? All right, so the barometric pressure has changed. Would the percentage of oxygen in that air change relative to sea level?
Yes.
No, isn't the
No?
percentage the
Yes.
same, but the pressure?
There you go.
Yeah.
Excellent. So why don't you explain that louder so everybody can
Just
understand?
the percentage of the actual partial pressures of each different nitrogen, oxygen, carbon dioxide is all the same, but you still got different pressures. So down here at sea level, you got higher pressure pushing it into your lungs. Whereas when you get up on top of the mountain, that pressure is no longer there, so you don't have the force actually pushing it into your lungs and into your bloodstream. It's kind of the same if you were to dive down, 100 feet, you have sort of something squeezing your lungs and pushing the oxygen into your vascular system.
Yeah, that's right. So it's going to be a function, but I do want to make sure we understand. So the percentages don't change, but the partial pressures do. So the partial pressure, because the total air pressure is no longer 760, by Dalton's law, each of the substituent partial pressures is going to be diminished dramatically too. So it's really it's really the PO2 that's diminished at high altitudes. And so again, getting back to how might you adapt, what would your body how might your body adapt to this, how might your physiology adapt? Do I? Yeah, your body might adapt in the short term by increasing the hematocrit. There also might be some central nervous system changes with the rate and depth of breathing that become rather chronic. If you've ever been to a very high altitude or talked to anybody that has, without the proper breathing apparatus and so on, you can become dizzy very quickly, lose orientation. Now, as I was saying, getting back to the anthropological aspect of this, the Sherpa actually have acquired a different anatomy. They have what are called barrel chests, and their ability to inflate the lungs is much larger. Once you go to South America, the folks living there, they look normal, but their blood chemistry is different. It's been changed. So as I say, there are different ways that humans have adapted to this type of life. So again, just three general things. Again, this is highly simplistic, but make sure you appreciate then that EPO can can increase hematocrit, that androgens, not computer operating systems, but that androgens, especially testosterone, can increase hematocrit. Yes, and a hypobaric, a low PO2 can also do that.
People who live in high altitudes tend to be of shorter stature.
That's true. I think that's true, although I'm not sure that necessarily must be true. In other words, that if I gave you the task of ascertaining the genetic causes of short stature at high altitudes, I think you'd be in a pickle because there's so many covariates. There's so many other factors that you'd have to control for the ethnicity and the background of the people from which they were descended and so on. And there may be nutritional factors. So in other words, while you may be phenomenologically correct, I don't think it's appropriate to argue necessarily that it's the hypoxia that causes the short stature. So any questions about EPO? Again, primarily important for elevating the hematocrit. We were talking about the Tour de France. There's a typical stage in the Tour de France that commences first stage, overcome allegations of doping. Some violators are netted. Tortuous series of, what is that? Rigorous denials, repeat cycle again and again, round of appeals, and so on. You buy out the media. So, who is skeptical? Now, again, the technology is changing. This particular athlete, and this was some time ago, was using something, continuous erythropoiesis receptor activator. So he was hitting it from the other end. He was basically using something that was, I presume, as I read this, was acting as an EPO agonist and producing the same result. All right, so we've talked about oxygen transport in our discussion of the hemoglobin. Let's talk a little bit about CO2 transport. Now, bear in mind that one of the fundamental differences between oxygen and CO2 transport is that inherently CO2 is much more soluble in the blood than is oxygen. So there probably is less need for specific trucks, specific transporters. There are 5 or 6 ways, 5 or 6 mechanisms by which CO2 is transported in the blood. We're really going to focus upon one, but there are 3 you should be familiar with. First of all, you should know that metabolic CO2, that is to say the CO2 generated by the respiring cells of the body, is transported in the blood primarily as bicarbonate. And we'll talk about how that happens, but depending on a variety of circumstances, we'll say that 70 to 85% of the evolved CO2 from respiring cells ends up as bicarbonate. Now, whereas only about 2% of the oxygen ends up in the blood, just sort of dissolved in the plasma of the blood, about 5 to 10% of the CO2 generated by the cells can be simply carried in the plasma and its molecular form, because again of the increased solubility of the CO2 in water. And then finally, and again, the 5 to 10% is varies with a lot of different factors. And finally, this other significant vector for evolved CO2, or what we're just going to call carbamino compounds. And by that we mean it really refers to protein binding of carbon dioxide in general, but most specifically hemoglobin binding of carbon dioxide. And once again, we're talking for the most part about 5 to 10% of the CO2 being bound to the hemoglobin. So you have several illustrations explaining this first reaction up here, and it's sort of stated here. I want to look at the illustration though at the bottom of this slide to maybe make it a little clearer. So here would be in the periphery, this could be skeletal muscle or whatever, generating or taking an oxygen and yielding and giving off CO2 at very high concentrations. First thing to notice then, that CO2 by simple principle of diffusion is going to diffuse from a region of higher concentration to a region of lower concentration. The region of lower concentration in this particular model is going to be across the capillary endothelium into the plasma of the blood. So you can see that first little blue CO2 there represents the migration or diffusion of CO2 from a region of high concentration to a region of low concentration, the blood plasma. Now, continuing with the diffusive gradient, it passes into the red blood cell, where there's even an even lower concentration of CO2. And then notice this reaction. This reaction is going to come up again. It's going to come up again in our brief discussion of the GI tract and in our brief discussion of renal physiology. The CO2 and water together will yield something called carbonic acid. That'll happen spontaneously at a fairly high clip, at a fairly fast rate in nature. But you have a whole family of enzymes in your blood. We'll just call this whole family carbonic anhydrase that dramatically accelerates the rate at which, and let's not worry too much about the biochemistry, the specific reaction here, because it's a little more complex than we have time to get into. But what's going to happen is the carbonic anhydrase is going to catalyze the conversion of CO2 and water together into bicarbonate and hydrogen ions, and carbonic acid is the intermediary. My point is, let's not worry about which aspect of this is actually mediated or the transition energy is affected by carbonic anhydrase. You start with this, carbon dioxide and water in the blood, and you end up with bicarbonate and acid as long as what is true, as long as there's a relatively high concentration of CO2 in the periphery. So at that point, the bicarbonate concentration building up in the red blood cell by diffusion is going to pass out of the red blood cell into the plasma. And then that takes us back to this. This is where that bicarbonate comes from by that carbonic anhydrase reaction. Once again, as long as CO2 is on the left side of the equation. Now, over here, we're in the lungs. So we have a high concentration. That's, I guess, the better way to look at this is that CO2 is being pushed out of the lungs, right? With each respiratory cycle, you're bringing oxygen in, CO2 is leaving. So that's going to reduce CO2 concentration in the plasma and drive this carbonic anhydrase reaction in the other direction. Again, because of this, maybe you should put an arrow here or something, this CO2 level is dropping. So once again, bicarbonate is abundant as it comes in the blood, as it arrives at the lungs. By diffusion, the bicarbonate now is going to pass into a region of lower concentration into the RBC. We have the carbonic anhydrase, the carbonic anhydrase reaction working in the reverse direction this time, yielding CO2 and water, and the CO2, as it indicated, will simply pass by diffusion into the region of lower concentration where it's expelled with each ventilatory cycle. So be familiar with that general sequence. We're going to also notice this little process down here. Notice that in general, as bicarbonate leaves, chloride is exchanging. So in this case, we have bicarbonate leaving, chloride coming in. That won't always be the case, but it's often the case that bicarbonate is exchanged across a membrane with chloride, and that's called the chloride shift. So any questions about that? I never know if you understand or just are asleep. Never know that about me, frankly. So we've basically made the argument that that in the venous blood, the blood returning to the lungs, there's a higher CO2 concentration. So it shouldn't surprise you that the pH of the venous blood is lower than that of normal arterial blood. And in part, that's a function of the CO2 concentration that you see there. Do you remember that if on a quiz I were to ask you which is greater, the oxygen diffusion gradient in the blood or the CO2 diffusion gradient, in which does the partial pressure change more dramatically? Oxygen or CO2? Oxygen. So remember that there's not a dramatic change in CO2 levels in the blood on the arterial side versus the venous side, but sufficient to cause a change in pH. Which brings us to this very, very important. I think it's both physiologically and medically very, very important diagram. You want to understand this one thoroughly. It's relatively simple, but be sure you understand this chart thoroughly. So in this particular graph, we have along the horizontal axis alveolar ventilation. Can somebody quickly define alveolar ventilation for me? How did we define that before? Yeah, good. Minute volume corrected for dead space. Minute volume corrected for dead space. And so this, you can see they've drawn a little dashed line there at about 4.2 liters per minute. And that should ring familiar to you. All right, in the vertical axis, we have alveolar partial pressure in millimeters of mercury. And so you can see they have a dot there and a dot there. Those numbers should be familiar to you as well. All right, these are the partial pressures that we came up rather extensively in our discussion of the carrying pressures of oxygen in the blood. But we actually have two lines in this graph. We have a red line and a blue line. Notice the red line is the partial pressure of oxygen, and the blue line is the partial pressure of CO2. So here's our reference point. We're going to say this is normal, whatever that means. That's going to be our normal rate of ventilation, breaths per minute times the tidal volume corrected for dead space. And so anything to the right of that, we're going to call, to one degree or another, hyperventilation. Anything to the left of that line will be hypoventilation. So what's going to happen? Explain to me what happens to the respective partial pressures of oxygen and CO2 as ventilation is increased, as we go into hyperventilation. Which gas increases, which partial pressure increases? Clearly oxygen, but as it does so, and this is important physiologically, as oxygen levels increase, as the partial pressure of oxygen increases in hyperventilation, notice what happens to CO2 levels. CO2 levels drop. Now we said there's a relationship between CO2 and pH, right? And so as CO2 levels in the blood drop in hyperventilation, what should be the change? How should the blood pH change? All right, it's going to go up. It's going to become more basic and more alkalic. Everybody see that? So there's going to be a physiological issue there. Now let's look at the other side of this, going into the hypoventilation. By the way, there's a term up here you should be familiar with, hypoventilatory hypercapnia. Hypoventilatory hypercapnia. Hypercapnia just refers to high CO2 concentration. But the two terms together are very instructive, because notice what happens in hypoventilation. Oxygen levels go down, and CO2 levels increase in the blood with respect to the partial pressure. That being the case, and CO2 levels increase, what should happen to blood pH?
Increase.
It's going to drop, right? It's going to decrease, blood's going to become more acidic. So if you think about it, and I invite you to do that, it shouldn't be too taxing, think about why this must be true. When I say it must be, there's actually another conceivable way to think about hypoventilation. But I think in remembering hypoventilatory hypercapnia, you can understand the relationship. But in hypoventilation, oxygen levels are dropping and CO2 levels are going up, and that's going to have a number of effects, especially on the ability of the patient to sustain their physiology, but also have an effect on blood pH. Any questions about this figure? There are a number of factors that are going to influence minute volume or the rate and depth of respiration. You have, for example, chemoreceptors. We'll talk a little bit about these in just a moment. Chemoreceptors that are sensitive to CO2 in the brainstem. You have some that are sensitive more to oxygen in the carotid bodies there along your in your neck. So as the ratio of oxygen to CO2 changes, that will induce a compensatory change in the rate and depth of respiration. As O2 levels go up, the rate of respiration might decrease. As CO2 levels go up, then the rate of respiration might change as well. The baroreceptors can also influence the rate and depth of respiration. They do so in a rather complex fashion. We won't get into that in too much detail in here, but basically, I think it's important to understand that there by those carotid body and carotid sinus, we also have in the aorta as well, baroreceptors that can also affect respiration. You have stretch receptors in the thoracic wall that limit the ability of you to inflate and deflate the lungs. This is sometimes called the Herring-Breuer reflex. There are several respiratory muscles, such as that serratus posterior that we talked about, that seems to provide some feedback, acts as a sort of little stretch monitor, tonus monitor, constantly monitoring the extent of stretch of those muscles and basically telling the brainstem how inflated the lungs are. Your breathing is going to be affected by a variety of irritants. I've heard somebody coughing in a fitful fashion this morning and sneezing. Certainly there are going to be interruptions of normal respiration. And of course, as all of these reflexes, as we consider all of these reflexes, you also have a CNS override. You can actually, when you talk, sing, or whatever, you can modify your rate of breathing in that fashion too. Has anybody ever heard of Ondine's curse? I think that's how it's spelled.
I thought it was Odin's.
I'm sorry?
Isn't it Odin's curse? Like O-D-I-N?
O-D-I-N, you like this? It could be. I thought it was Ondine. But either way, what do you know it to be?
You just cease respirations at night.
Why? Why don't they do it in the day?
Don't know.
Well, the reason it's a curse, whether it's spelled Ondine or Odin, I'll check into that. I thought it was Ondine. Ondine has a more rural flavor. Ondine, come on in here. Let's do some food. No, I shouldn't say. I'm going to give it but the implication here in Ondine's curse is a curse because they have to breathe voluntarily. Respiration is voluntary. So at night, respiration ceases because you're no longer providing the command, generating the voluntary signal necessary for that to happen. At least that's the implication in most severe cases. Again, you have that CNS override, breathing in, breathing out. Did you have a question, or you just?
Don't have anything to do with sleep apnea?
No, I think that's an entirely different process. Sleep apnea involve restricted airways based upon occlusion of the pharyngeal tissue when you're at rest or sleeping. So that I think is a little bit different. I mentioned the central and the peripheral chemoreceptors here. I think the way that we'll summarize this very quickly is that the central chemoreceptors are located in the brain, located in the brainstem, and they're most sensitive to pH. And we have to be careful here. They directly monitor cerebrospinal fluid pH. But no, where does the CSF come from?
Right.
It comes from the blood. And so what would cause the pH of the CSF to drop as the CSF is generated from the blood? Increased carbon dioxide. So just make sure you understand that the pH of the CSF in the brain drops, or at least in the brainstem. If it drops, it's likely to be dropping because the carbon dioxide in the blood around it is increasing. And these are by far the much more important regulators of respiration. We'll talk a little bit about these in just a moment. The peripheral chemoreceptors, those located in the aortic and the carotid bodies, very near where the neuroreceptors are located, these are more sensitive to oxygen. But having said that, they are only very grossly sensitive to oxygen. That is to say, in general, the PO2 has to drop. Whoops, there I go with my spastic writing again. They generally have to drop below 60 millimeters of mercury before these will kick in and cause a change in respiration. So you can see that what should the PO2 be in the blood? Yeah, 95, 100 or so. So that's quite a drop. So again, much more sensitive, much more important. These are sort of, I guess you might say, sort of an emergency backup. Let's take a break and we'll resume there.